Today, we are here with, I am addressing him, Dr. Jahangir. He has recently completed his PhD. He is my PhD scholar, 15th PhD scholar. In fact, he was motivation for total C2S program, Chip 2 Startup program. Whatever we are having this facility here as well as in the laboratory, that is called Chip 2 Startup program, for which he is main reason for this. One day he came to me that, sir, we wanted to do something. So we will propose something to the government of India. That's how we started. And then that time, big companies didn't believe us. Bitsilica believed us. Whereas other companies didn't believe us that we can do something. Later, once we got the project, now many companies are coming to us, including ECE. ECE also is going to do some work with us. So this is what what I wanted to tell is, once we are seriously working, I strongly believe we get the result. That's what. Only thing is we have to strongly believe is we have to work hard. That's the only one thing I strongly believe. That's what we believed it. We almost spent 6 months, and now Dr. Jahangir is well experienced in ABAM. It is very difficult to catch him, right? 1 hour, you will be afraid of, so much knowledge he has, how to gain it. But don't tell everything, right? So don't tell everything, only small things only you tell. So he is very knowledgeable. What I want to tell, it is not that one session we learn everything. We want continuous efforts from you. Osmania University is ready to accept all of you. Not that these 6 days, even later also. If someone is serious to work in the domain of VLSA, front end or back end, you are mostly welcome. Only your seriousness is very, very important. If you are seriously wanted to work, we can design the problem, or if you come up with a problem, we can work together. We will give the facility, right? So we can give the technical support. We can give whatever the thing, because we want something to be useful to the society, right? That is what the cause purpose we are here, right? So therefore, I don't want to take much time. So I am giving to Dr. Jahangir all the best.
Thank you, sir, for all the wonderful words. We'll do this session parallelly, okay, whatever we are going to, because it's a hands-on session. I think most of you have already used Cadence. It might be there in your labs, okay. The difference between the Cadence, what you are using and what we use is in the PD case, okay. PD case. I think you people have idea about PD case. PD case stands for Process Design Kit, okay. So generally, which is provided, the Cadence which is provided in universities and which you have in your institutes, generally it come up with a generic PDK, which we call it as GPDK, okay. So GPDK is mostly for understanding purpose and it is mostly for learning purpose, okay. Once you have designed anything using that particular PDK, you cannot send it to any fabrication lab. It cannot be fabricated, okay. So if you want to design something which has to be fabricated, you should first get the PDK from that particular fabrication lab, okay. And we don't have much fabrication lab in the world. As you all know, most of the fabrication lab are concentrated, okay. The famous one is in Taiwan, TSMC, okay. And then you have in China, Korea, and to some extent in Israel, okay. And some industries have their own fabrication labs, which they don't share with others. Now in India also we have a fabrication lab, which is called as SCL, okay. Semiconductor Laboratory. Actually it was originally part of ISRO, which fabricated the chips of ISRO originally, but now it has been open under Semiconductor India program to fabricate for the industry startups as well as for the institutes through C2S program. So therefore, first thing what you need to do if you want to fabricate anything is to acquire that particular PDK. So for that, they will not be directly giving you PDK. You are supposed to pay some fees if you are going for fabrication outside. Then there will be some amount which you need to pay there, and you need to sign what is called as an NDA, non-disclosure agreement, and then you will have access to that particular PDK. In the similar manner, we have also done this PDK. Anyway, there is no fees for that. Under C2S program, it is provided free of cost to us, and we have signed the NDK, and that is why the SCL PDK is available here, and we'll be using that to fabricate our ICs. The only problem what you have here is you don't have advanced technology nodes in this fabrication, fab lab. Okay, it only fabricates presently 180 nanometer. There are provisions or there are plans to improve that or go to the lower technology nodes. But as of now, we have only 180 nanometer. You will probably see if you can cooperate, all of you, if you can cooperate and do it as fast as quickly as possible, we will be able to cover up to GDS. Okay, you will be able to understand the complete flow, or else if we don't have time, we have to stop somewhere in the middle. Okay. So if you can cooperate and do it quickly, we should be able to get up to GDS. You will be understanding on the entire flow. So we will understand with a very basic, analog circuit which we are going to discuss here. It's a two-stage op-amp. I think most of you might have studied it in your classes, PG or UG classes. Okay, and op-amp is the very basic circuit which we are going to use for analog IC designs. You might have studied subject like linear IC design, where you have used op-amp for doing a lot of different operations. Okay, adder, subtractor, differentiator, integrator, filters, and all those things. Basically, as gates are important for making any particular block in digital, similarly op-amp is important to make any particular analog circuits. Okay, let me drop that circuit again for reference. This is what a basic two-stage Miller op-amp would look like. So you have a differential stage, then you have a common source amplifier there. Okay, it's a two-stage, so therefore we call it as a two-stage amplifier. Then you have a biasing circuit which provides the necessary current for these two amplifiers. And then you have a Miller capacitor to stabilize this particular op-amp. And ultimately, because you are making an IC inside, this op-amp will be used inside IC and not outside that. So most of the loads what you are going to experience are going to be capacitive load. Okay, so you design it for a specific capacitive load depending on a given specification. Okay, if it is not meant for capacitive resistive load, then you need to add one more stage here. Okay, the important parameter or specs which we design for is slew rate, because as I said, the maximum load here is going to be a capacitive load. So therefore, we measure its performance mostly based on slew rate. The other parameters what you have is phase margin, which speaks about the stability. Generally, we try to maintain 60 degrees of phase margin in most of the circuits. Then the other specs are ICMR, which talk about the common mode voltage which you apply to the input, what is allowed for this particular circuit. Then other things you have UGB and all those things. But these are the main things. As UGB and CMRR, all those things are there. The top three things is what we concentrate in our design. We have already, based on these particular specs, there are already a lot of methods I think you might have studied in your theory or in your textbooks. Alan Hallberg textbook, if you read, he will give you a clear-cut picture of how to design this two-stage op-amp. Designing two-stage op-amp is all about finding out the values of these W/L ratios for your given specs. Okay, based on whatever is the biasing current given. Okay, so I'll not go into that particular procedure, but that itself will take a lot of time. We'll be mostly concentrating on how we are going to implement this in the tool. So based on these particular specs, we have actually designed it for a slew rate of 10 volts per microsecond and 60 degrees phase margin. And our ICMR was from 0.6 to 1.6 volts. And we are operating with a VDD of 1.8 volts. Okay. So again, in SCL technology, there are different types of transistor which you can use. You have 1.8 volt transistor, 3.3 volt transistor, and 5 volt transistor. 0.6 to 1.6. These are the specs of the op-amp what we have used. Based on your application, it may vary. So based on this, we have actually calculated the W/L ratios of all these transistors. Okay, I am not going to go into the theoretical procedure, but I will let you know what is those values. And we will try to design, again, schematic, starting from the schematic design. MOS varactors, okay, where you have the source and drain shorted, source, drain and body is shorted, and the gate terminal is shorted, and this acts like a capacitor. These are, we call it as accumulation capacitors. Again, there are different types of accumulation capacitors. You have accumulation capacitors working at 1.8, 3.3 and 5 volts. The different varieties are there. And the other capacitor which you have is a MIM capacitor, metal insulator metal capacitor. And then when we talk about resistors, we have got poly resistors, which are generally used, okay, which actually give you a resistance of MOPO resistor. This is also called as MOPO resistor, which actually gives a resistance of 1 kilo ohm per square. Okay, similarly, if you want lesser resistance, then you have metal 1, metal 2 resistances are there. You can use those resistance to get lower resistance. So these are broadly the features of for our specs. We have decided to go with 1.8 volts VDD. So therefore, we will be using all those transistors. What we will be using here will be 1.8 volt SCL transistors. And wherever capacitors are required, we will be going for MIM capacitors. The difference between MIM and accumulation type of capacitance is, accumulation type of capacitance will take smaller area because it is based on MOSFET, but it is non-linear because MOSFET can go from the linear region into saturation region. Okay, that means the channel can go from depletion to accumulation based on your voltages. So therefore, you don't have any fixed or accurate capacitance from this particular capacitor. Whereas MIM capacitor, they are very much accurate. Demonstrate how we are going to open it. There is a little bit difference between how you launch a normal cadence and how you are going to launch this particular thing. Okay, so we will be launching this by setting SCL as our the library. Okay, so for that some steps you need to follow. Actually, there is a special folder which is created inside, okay, which contains a special CDS master file. Okay, based on that library, what you are going to use for all your design is going to be TSL. You will have access to this SCL technology, SCL library, by following this particular procedure. So the first thing what you will be going is you will be typing the CD space OU underscore SCL PDK underscore projects, which is in small letters, PROJECTS. Now from here you can launch your this thing, but the commands are different. Okay, so first you have to enable the C shell CSH. Then after that the next command is you have to run that particular source file. Okay, source space dot backslash PDK underscore flow underscore setup dot CSH. Yeah, if you have successfully typed this, you will be able to get this message: SCL PDK flow setup with cadence virtuoso is complete. The next command is this command. You will be typing this command: CDS project, CDS PRJ space projects. Next is the normal the cadence file which you will be sourcing: source space backslash home slash install slash CSHRC. So we'll create a new library now. So the procedure is you go to file, new library, and here you can give whatever name you want for the library. Okay, we are giving op-amp OU as our name, and after that you have to click on attach to existing library. Okay, attach to existing technology library, and then click on OK. Once you do that, you will be getting the list of all available libraries. Just scroll down until you find this TS018 underscore SCL. TS018 underscore SCL is the SCL library. So with this, our library is created. You can view your library by going into library manager. That you can find in tools. Go to tools and library manager, and there you should find your library. Here we have declared it as op-amp OU. So right now there are no cells in this particular library, you can see there, and create a new cell view. Go to file, new cell view. This pop-up will appear. You have to select your library, whatever you have created in previous step. Whatever library name you have created, select that library, and after that give some cell name. We will call it as op-amp. So select your library, give your cell name, and make sure that the type is schematic. Click on OK. You will get some warning. Just click on that session. If you get any warning window, click on session. Red color it will be marked. Okay, once everything is successful, you should be able to launch this particular tool. This is schematic editor or virtuoso. Okay, so once you are into this particular schematic editor, then you can draw the schematic what is present here using 1.8 volt NMOS and 1.8 volt PMOS transistors. These M1, M2, M5, M7 and M8 which are shown here are NMOS transistors. M3, M4 and M6 are PMOS transistors. Both those transistors, we will be choosing 1.8 volt transistor from SCL technology, and we will be drawing this schematic. How you will be finding that transistor is, click on the new instance, that is new instance. He is showing that with the arrow. Okay, that is the new instance button. Once you click on that, a new pop-up will appear, and from here, you are supposed to use this NMOS transistor. So library, you select it as SCL library, which is TS018 underscore SCL. Select that library. And inside that library, you can see the cells. So once you type NMOS, you will find all the different types of NMOS. You have to select NMOS underscore 18, it will be written. So you select this transistor just click on close. You will be having the transistor. You can place the transistor wherever you want. Okay, so like this, you can select all the different transistor and start creating this circuit. Okay, now I ask Ali to do the remaining circuit. You people can also follow. Just look at him and follow how to draw this circuit. Now Ali will be creating this entire two-stage op-amp schematic in this particular tool. Okay, and he will be choosing the transistors from SCL technology, and he's just clicking using that create instance button and then creating it. Just look at what he is doing. Afterwards, we will repeat it again. Yeah, please follow it. You can have a look at your Google Meet or on the projector. Those who can draw this particular schematic, and what we'll be doing to the body terminals is all the PMOS bodies has to be connected to VDD, and because it's an NVL technology, so therefore all the NMOS's body has to be grounded. As of now, we will just create pins, VDD and ground pins. Later on test bench, we will create the ground edge. But you make sure that it is connected to VDD pin, body of PMOS, and body of NMOS to the ground pin. Yeah, now we have completed with all the transistors. We have placed all the transistors. We have wired them up. Now let us place the capacitor there. So we'll be using a MIM capacitor again from the 180 nanometer SCL technology. CMIM. CMIM is the name of the capacitor. Once we have completed the schematic, now we need to place pins on that so that we can access those terminals. Pins, you will find it again on the top. There is a pin icon. Okay, this is the icon, pin icon.
For now, what we will do is we will decide the direction of the pin, and we can select input pins, we can select output pins, and the thing is, for ease, we will use the input output pins so that we can use them as inputs and out.
Yeah, now we can place the pins. You have to select the direction of the pin, and you have to also mention what type of pin you are placing, whether it is VDD or ground.
So we will take VDD, and we will press space. We can assign multiple pins at once. So what we'll do is we will write the name of the pin, we will give the space, so it will select one pin at once. For now, I think you guys should see this, then we will try doing it again. So for now, just see this and note the steps.
Okay, as I said you earlier, a preferred book is Alan Hallberg. You can just see the procedure of how to design that using Alan Hallberg, CMOS IC design. Okay, so we have already done that. So we will be replacing these default WBL ratios with our WBL ratios. You can show the WBL ratios what we will be using.
The WBL ratios for differential pair will be 0.22 and 0.5 as width and length, and the fingers we will using as 5 and multipliers as 1.
Yeah. One thing what you need to remember is the default value length of this particular transistor is 0.18. But when you are doing analog design, we should not keep it at 0.18. You will be increasing the length of the transistor. Okay, the reason for that is, short channel devices have channel length modulation. So if you want to minimize the channel length modulation, you are going to choose the length of the transistor as much long as possible. Okay, so here we have not gone with the default 0.18, we have increased it to 0.5.
In order to change the properties and widths and lengths of the MOSFET, what you can do is you can select the MOSFET and press Q. Or you can do one thing else, you can right click and then go to properties, and then you can find this menu. From here you can change the fingers and WBL ratios and etc things. For now we will be taking is 0.22 and the length as 0.5, and the number of fingers you can select here. We are taking it as 5 and the multipliers as 1.
And one more thing we need to remember here is in SCL PDK the default scale is micrometers. It's a micrometer scale. That is why it is 0.5. You select the MOSFET, press Q. Once you press Q, you will be seeing these properties. In the properties, you will be able to modify the W and length of the transistor. Okay. Just delete the W and enter your W whatever you have designed.
First you have to select the MOSFET, then you have to press Q. You can note down the values from here, from this Excel sheet.
Yeah. Create cell view from cell view. So like this you will be creating the symbol for this.
And this window will pop up, then you will select OK. And now you have to assign the pins to the sides. You can assign the pins to the left, right or top or bottom. Usually what we do is we'll assign the VDD and ground pins on the top and the bottom, and the rest of the pins we'll assign the input pins on the left side and the output pins on the right side.
Yeah, we are now keeping the pins at the appropriate sides. Okay, inputs we'll try to keep it on the left side for our symbol purpose. Okay, it is not hard and fast rule. Wherever you would like to keep it, you can keep it. Yeah, once you have done with this, you can press OK and remove this rectangle. And then there is a polygon there. You can take that particular polygon and draw a triangular shape, the shape what we are familiar with for the op-amp, and you can align the pins. This is how we align the pins, VDD and ground. Okay, boundary, then you have to adjust the boundary such that half of the pins, red color pins, are inside and outside. Half of them are outside, half of them are inside. Okay, or else you will not be able to connect them. Yeah, once you have saved the symbol, now we will create a test bench for this. For that you can go into a new schematic. Okay, we will call it as op-amp test. Right, now here you have to place the instance of the design what you have created. Go to your library, click on create instance, go to your library and select the op-amp what we have created earlier. Okay, and view should be symbol view. You make sure that the view is symbol. Yeah, you can see the symbol what we have created here. You can place it here. And now we have to assign power supplies to this. This power supplies what we are going to assign it, you will be finding in analog library. Select analog lib, and from there give first power up the device. Select DC power supply VDC, and for current we will be selecting I bias. Okay, and input signals we have taken two sinusoidal signals, V sine. Right, now connected as required. VDD you will be giving to the VDC DC power supply. The two input signals will be collecting to V1 and V2. Okay, and I bias you collect it connect I bias between VDD and actually this current has to be provided by a current mirror inside, but instead of drawing that going into the design of current mirror, we are just concentrating on op amp. So that is why this current is taken from outside. We are taking an ideal current source for this purpose, right? Even your DC power supplies has to be grounded and your signals has to be grounded. So select ground pin and connect it to your power supplies.